Okay, let's work on section 2.4, the chain rule. Man, if you thought the power rule was great, it's got nothing on the chain rule. So, chain rule, wonder what that's all about. Well, have you ever played the game of Mousetrap? And you know how, like, if you trickle one thing, this is going to come down, and then it's going to cause this to float down, and just a lot of chain reactions. And that's kind of what happens on our chain rule, is we have many things triggering subsequent derivatives. So the chain rule is used to differentiate composite functions, functions that are other than just like a trivial x within other functions. So here's the type of functions that chain rule will now allow us to differentiate. We've worked with all of these types of functions, nice, simple, x squared minus 1. We can handle it using the power rule. And now with the chain rule, what we can do is we can add an additional function on there. So you can see how this has been built up of, like, let's say that, let's do it in g instead. G of x was equal to x squared minus 1. And then f of x I'm going to define as the square root of x. If I wanted to, I can make this as f of g of x, which is a composite function. And that would say, let's put g inside of the f function. So it would look like, here's my g of x going inside the square root function. And that's a composite function built up of really two functions there. So the question is, how do you differentiate something like that? Well, we use the chain rule. And then over on the left here, you can see we've been able to do sine of x. Now we're going to be able to do sine of 5x, where it's no longer just single x, but 5 times x. We've been able to deal power rules, taking us through 3x minus 2. Well, what happens if I make it a power of 7 outside of 3x minus 2? Composite function. There again, I could say g of x is 3x minus 2. There's my inside function. I'm going to make my outer function then just something to the 7th. And if I say f composite g of x, do some fancy writing there, different way of writing a composite, then it's g within f, isn't it? So my g function will slide inside my f function, and I have 3x minus 2. So composite functions, we need to be able to handle differentiating those. Here is the theorem about the chain rule, and it says if y equals f of u, and it is a differentiable function of u, and let's say u equals g of x is a differentiable function of x, then y would equal f of g of x, basically building a composite function. That will be a differentiable function. If the outer function and the inner function are differentiable, then the entire function, the composite function, will be differentiable. And here's how we do it. This notation may not make the most sense, but what I would do is work on differentiating this one with respect to u, so dy du, and then my other one, du with respect to x. With this notation, you can see that du over du cancels out and gives us a dy dx. Okay. Otherwise, if you like this type of notation, what it's saying is we will be able to take, so if I take f of g of x and I want to take its derivative, that will be equal to the derivative of the outer, so the derivative of the outer function f, and I'll leave the g of x alone, multiplied by g prime of x, the inner function. It really, the theorem makes it look more complicated than it really is. Basically, the chain rule says to multiply the derivative of the inside function by the derivative of the outside function. So let's try some examples. First off, we're going to start with f of x equals 2x plus 3 quantity squared. We can do it with and without the chain rule. Without the chain rule, you could handle this. We would just take f of x 2x plus 3 quantity squared looks like 2x plus 3 times 2x plus 3. FOIL that out, we get 4x squared plus 6x plus another 6x. Oh, let's just call that 12x then, plus 12x in the middle, plus 9. Now if I go into its derivative, nice easy power rule application. So 8x plus 12. We love it. Easy to do. What about using the chain rule? How does that differ? Well, what I'm going to do is first I'm going to talk about how this is a composite function. And I'm going to let f of x be my outer function. And that's just going to be something squared. And then I'm going to set up g of x to be my inner function, 2x plus 3. Well, based on the chain rule, here's my structure of my composite function. It's g of x inside f of x, so f of g of x. The derivative of this, if we look on that previous screen, or if you look above in your notes, it says take the derivative of f of x, leaving g of x alone, and then multiply it by g prime of x. So I'm going to take the derivative of the outer function, which is a squaring function, right? So let's write 2x plus 3 squared. Its derivative is going to be equal to, first we're going to take the derivative of f, and my f function is this right here. So the 2 is going to come down, and then I'll subtract 1 from it, correct? So the 2 comes down, and I get x something raised to the first power, because 2 minus 1. It is structured with the inner function inside it there. So I leave the inner function alone. It'll be 2x plus 3. Then I multiply by g prime of x. And g prime of x, here's my g function. It will be multiplied by 2. So I'm going to get a final answer of 4 times 2x plus 3. Distribute the 4, and I'm at 8x plus 12. The same answer that I got when I did it without the chain rule. Okay? So you got to think of these inner and outer function. It's kind of like peeling the skin off an onion, if you will. So the derivative of the outer function times the derivative of the inner function. Let's find the derivative of this one. What is our inside function? Well, on this one, here's my inner function, 4 minus x squared. My outer function is taking something and cubing it. F prime of x is equal to, let's take the derivative of the outer function. And the outside function is a cubing function. So I'm going to have 3 and then a power of 2. 3 comes down, and then I subtract 1 power from that, and it brings me to a power of 2. Inside that, I evaluate it using g of x. So g of x goes in there, and what is my g of x? It's my inner function, 4 minus x squared. Often I think of this as just take the derivative of the outer, so 3 comes down, changes to a 2, and leave the inside alone. So here's leaving the inside alone. Multiplied by, here's the chain reaction now, the derivative of the inside function. And the derivative of the inside function will be negative 2x. And finally, let's clean this up. So I'd have negative 6x times 4 minus x squared. And I think that's a good spot to leave that function at. Rewriting can sometimes be an advantage on these, so let's rewrite. It'll make the outer function maybe more apparent to us. And looking at this one, I have a power of 3, an index of 2, so this will be x squared minus 1 raised to the 3/2 power. Can you identify the outer function? The outer function is something raised to the 3/2. The inner function will be x squared minus 1. So thinking about the chain rule, I'm going to start from the outer function and work my way in. The outer function being the power of 3/2, so 3/2 comes down. It switches to a power of 3/2 minus 2/2, or 1, right? That's really a 1. So this is going to leave me 1/2. 3/2 minus 2/2 leaves me 1/2. That was the derivative of the outer. Now, I evaluate that and I leave the inside alone. The g of x goes inside there. Multiply it by the derivative of the inner. The derivative of the inner is 2x. And simplifying, I can take 3x, or 2x times this 3/2, and that will look like 6 over 2, which is 3x square root x squared minus 1, just rewriting that 1/2 power back into radical form. Work from the outside, moving to the inside. Number 4, let's rewrite. And this time, I see that it's coming from the denominator, so I'm going to have -7 times 2x minus 3 raised to the power of -2. The -7 is not really going to interfere with anything. It's just a multiplier. It's that scalar. So I'm going to consider my outer function to be this -7 times something raised to the -2. And my inner function is going to be the 2x minus 3. First, start off by taking the derivative of the outer. The derivative of the outer means the -2 comes down, multiplies by the -7, and I'm going to have -2 minus 1. Leave the inside alone, and that inside was 2x minus 3. Chain reaction now. Take the derivative of the inner. The inner was 2x minus 3, so the derivative of that is simply going to be 2. Now it's just cleaning it up, making it look nice. 14 times 2 will make 28. And that's over a -3, or with a -3 exponent, so I'm going to push it below and write it as a positive. There is our derivative, utilizing the chain rule. I just have a lot of practice for us. Okay, rewrite this. Maybe hit pause, see if you can rewrite this correctly. I can rewrite it as 2x minus 3 raised to the -1. You know, a thought just occurred to me here. Is there any reason why I couldn't use quotient rule on this? You might be asking yourself that. And absolutely not. You could use quotient rule. We're just going to show you there is an alternative. We can use the power rule, or not the power rule, but the chain rule. Do you see the outer function? Outer function is the -1 power, something to a -1. The inner function is the 2x minus 3. So derivative of the outer function will be -1, and then it'll go -1 minus 1, shifting it to a -2, right? Leave the inside function alone, so 2x minus 3. Now a chain reaction happens, and we chain off, and we take the derivative of the inner function, and the derivative of that is simply 2. Rewrite it so it looks nice, and we have -2 over 2x minus 3 raised to the 2nd. I don't know about you, but I think that is a little bit easier probably than doing quotient rule. Number 6. Can you pick out the outer function? outer function is something raised to the 2/3. The inner function is 5 minus 4x squared. Where do you start? Let's start with taking the derivative of the outer. 2/3 comes down, and then I'm going to have 2/3 minus 1, which would be like 3/3. Leave the inside alone. 5 minus 4x squared. You should only ever be doing like a power rule one time in that first step, or changing a trig function. There should only be one derivative being taken at a time. Now, next step is I want to take the derivative of the inside piece, which I could look over here as well, or I should look up here. There's the inside. And the derivative of that is going to be a negative 8x. Simplify. Negative 8 times that'll be negative 16x over 3. And then I have 5 minus 4x squared raised to the negative 1/3. That will look like negative 16x over 3 cube root of 5 minus 4x squared. There's our y prime. Problem number 7. Getting the hang of these? All right, let's see. Probably let's start with a rewrite of this. Y equals negative 2, just a multiplier, times 6x plus 3 raised to the 1/3. Ooh, but it's a negative 1/3. Caught it! I bet you thought I was going to miss that. All right, we got outer function. Our outer function is that negative 1/3. And you know what? I think I'm going to put that negative 2 in front so I don't lose track of it. My inner function will be the 6x plus 3. So here we go with the chain rule. Derivative of the outer function. The negative 2 gets multiplied by the negative 1/3, which will give us something raised to the negative 1/3 minus 3/3. That inner function was 6x plus 3, so we leave the inside alone. Now, chain, and I'll multiply by the derivative of the inner function. Our inner function, the derivative of it is 6. And we're in the cleanup phase, so I'm going to have 6 times 2 will be 12, divided by 3 is 4. And this will become what? A negative 4/3 power, which says drop it to the bottom, and I'd have the cube root of 6x plus 3 raised to the 4th. There's our y prime. And problem 8. Is this our last one? Oh gosh, not quite, huh? We got a couple to go. Rewrite. So my outer function is a negative 3 raised to the positive 1/2. My inner function is an x squared minus 3x minus 4. Derivative of the outer is negative 3 times the 1/2, power rule going on. 1/2 minus 1 will give me negative 1/2. Leave the inside function alone. Now multiply it by the derivative of the inner. The derivative of the inner is 2x minus 3. We essentially have it done. It's just a matter of cleaning it up. So I get negative 3/2 times 2x minus 3, which would be like a numerator. And then my negative 1/2 will push that function to the bottom. And really nothing to clean up. I guess we could push that negative 3 through and get negative 6x plus 9 divided by 2 radical x squared minus 3x minus 4. There's your y prime. Okay, two final ones. Oh my, huh? This will be a fun one. So let's do it using the chain rule because I can think of a couple ways to do this one, but let's use the chain rule. So the outer function is something squared. The inner function, like my g of x, is an x minus 1 over x squared plus 3. Do you see quotient rule coming our way? I do. So f prime of x will be, let's deal with that outer function first. 2 comes down, leave the inside alone. This will switch to a power of 1 by the power rule. Leave the inside alone. Not done yet because we haven't taken the derivative of the inside piece. The derivative of the inside piece becomes a quotient rule. So derivative of the top multiplied by the bottom minus derivative of the bottom times the top over bottom squared. And that was all quotient rule. So we've done our derivative. It's just sitting in a very, messy state here. So let's clean up. 2 times x minus 1 over x squared plus 3. That power of 1 we could just erase, couldn't we? Ignore. Not necessary to write. On the other, I think I'll leave these as individual fractions at this point. X squared plus 3, quantity squared. On top, we have an x squared plus 3 minus 2x squared plus 2x. Well, that certainly can be cleaned up. And while I'm cleaning that up, I think also I'm going to try and pull this together. So because it is multiplication, that's nicer than having addition, because with addition we got to have like denominators. With multiplication of fractions, we do not. So here's what we've got. 2 times x minus 1 times, let's clean up our top here. The 2 will be negative x squared plus 2x plus 3, written over a denominator of x squared plus 3 raised to the third power. Here we had a power of 1. On the other we have power 2. Add the 2 together and we are done. Very nice. All right, this one looks extremely interesting, doesn't it? The outer function, there is not a big outer function on this. What I see as going on my main part of this is that I have this quotient rule coming in. So I think the quotient rule is what I'm going to deal with first, and then within that we're going to have probably a chain rule. So let's rewrite this real quickly as x over x squared plus 4 raised to the 1/2 power. And we are just going to proceed with our good old quotient rule, which becomes f prime of x equals derivative of the top, which is 1, multiplied by the bottom, cube root x squared plus 4. Subtract derivative of the bottom. Okay, I don't want to look here. I want to look over here where we rewrote it. Notice we have an outer function of 1/2. The 1/2 comes down. I get x squared plus 4 raised to the negative 1/2. There's the power rule. I subtracted 1. Now I need to chain off and multiply by the derivative of the inside piece, which is 2x. And then don't forget to multiply by the top. So here's, what do I want to say, quotient rule in action. Derivative of the bottom multiplied by the top function. Okay, let me erase that so we can get our division sign going. Divided by the bottom squared. So I'm going to have x squared plus 4 raised to the 1/2. And this is all g of x getting squared from our quotient rule pattern. Well, that made a nice denominator, didn't it? Denominator cleaned up nicely, x squared plus 4, because 2 times 1/2, power to power means multiply, gives me a 1. What does that leave us on top? I've got a cube root of x squared plus 4. The half and the 2 multiply to 1, and I get an x squared, so we got minus x squared numerator. The negative 1/2 will move that to the bottom. Did I screw up? I certainly did. I am so sorry. Do you know where I screwed up, you guys? You probably caught it way back there. That should have been a cube, shouldn't it? And we are so far into this video that I want to just make the corrections here, and I hope you can follow. I'll make them in pink. This would have been a 1/3 power, and 1/3 comes down. So I'm going to have 1/3 there. 1/3 minus 3/3 will land us at negative 2/3. So let's clean this up as a negative 2/3. Derivative of the inside is perfectly fine. That'll stay as a 2x. However, it's not getting canceled anymore. And then multiplied by x. That first step now is cleaned up. I will have the bottom is not going to be quite that nice, will it? Because this would have been a 1/3 power here. So this would have been to the 1 raised to the 1/3 and then squared. So on my bottom now I have x squared plus 4 raised to the 2/3. Liking that. The minus part, now we're focused in right here, doesn't clean up quite so easily, does it? So erasing this. Hope you did this in pencil. 2x times x gives me 2x squared. The 3 stays in place from there, and then this negative is going to move it down below. So I'm going to have cube root of x squared plus 4 raised to the second. Now, ideally, we should really get the top into a fraction that works all together. But I know this video is getting pretty long, so I'm going to leave it there. And in class, we will take it one step further. All right, that leaves us with the homework, and the homework looks like 1 through 12. All you need to do, guys, is remember derivative of the outer first, leave the inside alone, and then multiply by the derivative of the inside.